So our next speaker is Nariyoshi Chida, who's going to tell us about repairing regular expressions for extraction. Take it away.
Hello, my name is Nariyoshi Chida from NTT. I'm going to talk about repairing regular expression for extraction. This is a joint work with Tachio Terauchi from Waseda University. This talk is about regular expressions, so let's talk about regular expressions a little bit. Regular expression is a pattern that describes a set of strings, and regexes play a crucial role for membership testing and extraction. In both cases, the input is the same, so the input is a regex and an input string. But the output is different. In the case of membership testing, the output is true or false, which means that the regex accept the input string or not. In the case of extraction, the output is substrings or false, and this means that if the regex accept the input string, then the output is substrings extracted by the capturing groups. And false means that the regex rejects the input string. As you know, regular expressions are ubiquitous, but despite the widespread use of regexes in practice, there's a problem. The problem is regular expressions are difficult for the reasons. This is a problem because if we incorporate an incorrect regex into a program, then it may become a bug of the program. In more serious cases, it may become a vulnerability of the program, so this is a problem. So to overcome this situation, prior works try to automate the task. However, these prior works focuses on only regex for membership testing, and none of them can handle extraction. But does it mean that extraction is easy? The answer is no, actually. This is because extraction is more difficult than membership. This is because in addition to the difficulties of membership testing, extraction has a unique difficulty called deterministic behavior. To describe this, let's see an example. So in this case, from the perspective of membership testing, it is easy to see that the regex accept the input string. But the question is, which substring is extracted by the capturing group? One may think that the substring AA from position 3 to 4 is extracted. But the actual result is A at position 4. Why this substring is extracted? That's due to the deterministic behavior of regex engines. And this is a real problem, and many people suffer from the behavior, so we want to automate the task. And in this talk, I introduced a tool called R3 that automates the task. And R3 is a programming by example tool, so it takes examples as an input. And in this case, there are two types of examples, positive one and negative one. And a positive example is a string to be accepted with special parentheses that denote substrings to be extracted by the capturing group. And for example, this positive example means that the regex that I want should accept the input string AAA, and it also should extract the substring AA from position 0 to 1 by the first capturing group. And a negative example is a string to be rejected. So once we input the information into our tool R3, then R3 output a correct regex. And the correct means that the regex extract correct substrings from all positive examples, and it rejects all negative examples. So we do not need to repair regex for extraction manually. And one of the important points of this work is here. So our tool R3 supports real-world extensions. This point is important because if we do not allow to use them, then there are unsolvable program instances. But if we allow to use them, then every program instance has a solution. So this point is important. So now I'd like to describe our repair algorithm briefly. And at a high level, our algorithm builds on the existing method for membership testing. So it consists of 3 components here, and this. But in this talk, I'd like to talk about the first and the last one. In the first step, we generate a template. A template is a regex with holes, and a hole is a placeholder to be replaced by a concrete regex at the final step. So we change the structure of the given regex with holes like this, and try to find a template that can be a solution. Then, in the final step, we check whether the template has a solution or not. And to check this, we try to fill the holes with a set of character for satisfying all examples. But the question is, how to define the set of character? Or is it impossible? And to check this, we simulate the matching of this on each example and collect the information for satisfying the example as an SMT constraint. And if the SMT constraint is satisfiable, then we have a solution. So we construct a set of character from the assignment to the formula. But if it is not satisfiable, then the template cannot be a solution at this time. So try the next one. So this is a brief overview of our algorithm. But to achieve these procedures, we need to address some extraction-specific challenges. One of the challenges is this. So to generate an SMT constraint, we need to simulate the matching, but how to simulate the matching? To simulate the matching, we need a deterministic semantics of real-world regexes, but we do not have such semantics. So this is a summary of our challenges and contributions. The first one is about the semantics that I described before. And the second one is about the search space, and this is related to the pruning techniques. And we address these challenges like this. And in this talk, I'd like to talk about the first one, and I will not talk about the second one, but you can find the detail in a paper. So now I'd like to describe how to define the semantics of real-world regexes. In the case of non-deterministic semantics, we can define the semantics like this. So this part represents a state of regex engines, and this part is the matching result. But this is a non-deterministic semantics, so if a regex has an ambiguity, then it may output multiple matching results, like this case. But our setting is extraction, so we need to find out the actual matching result from the matching result for correctness. But how to find the actual result? To find it, we need to disambiguate the matching, but then how to disambiguate the matching? The idea is to use continuation. This idea is inspired by Sakuma et al. For pure regexes. And to describe the idea, let's recall the example and focus on the union. This union is ambiguous because both matching can succeed. But we know that the union matches the character A. But why not AA? That's because if we choose AA, then the remaining matching fails. Because the remaining matching require consuming at least one character A, but if we choose AA, then the remaining character is the empty string, so we cannot consume a character. So we have to choose the sub-expression A. So in this case, we can disambiguate a union by checking the result of the remaining matching, that is continuation. And in a similar way, we can disambiguate the matching. So more precisely, in the case of deterministic union, we can model the behavior like this. So this is actual behavior of deterministic union in the actual regex engines. And to model this behavior, we use this idea. And I'd like to describe the idea by using this example. So in this case, I want to disambiguate the union. And to disambiguate the union, we first perform the matching of AA and the continuation. And if the matching succeeds, then we choose AA. And otherwise, we choose A. And this behavior is actually consistent with the behavior of regex engines in the real world. And then I'd like to describe the case of real-world regexes, and this is a behavior of positive look-ahead. So positive look-ahead checks the pattern without any character consumption. And also, positive look-ahead some tricky part that we have to think carefully. And the point is here. So once we move outside of the look-ahead, then we do not backtrack to the inside of them. So for example, in this case, this regex accept the input string AA if we can choose the sub-expression A. But to choose the sub-expression A, we need to backtrack to the inside of the lookahead because the union first performs the matching of AA, but the matching succeeds, so we move outside of the lookahead, and the remaining matching fails, so we want to backtrack to the inside of them to choose the sub-expression A, but we can't, so the regex rejects the input string. But from this case, we can see that the continuation do not affect the matching in lookaheads. So to model this behavior, we ignore continuation when entering lookaheads. So this is semantics of, this is a definition of our semantics. And this part is a state of regex engines, and this part is the matching result. So we have some extensions for handling real-world extensions with determinism. For example, D is a direction for look-behinds. We need this because the look-behind changes the direction of the matching. So to know the current direction, we use direction D. And so this means that if we run the matching with this state, then the output is this. And this is selected rules of our semantics. I do not describe detail, but you can find the detail in our paper. So based on the semantics, we can define the method for generating an SMT constraint. So in a similar way as that of the semantics, we use continuation for disambiguous matching. And we check whether which character should we add to the set of character for satisfying examples. Okay, finally, I'd like to show the evaluation. We have conducted some evaluations, and in this talk, I will show the result of efficiency. To measure the efficiency, we need a data set, but unfortunately, there is no standard benchmark for our extraction. So we prepared a data set from GitHub. More precisely, we used GitHub Advanced Search with keywords, regex, extraction, bugs, and so on. And we check whether commit is about bugs of regex for extraction or not. If so, we correct the regex as an instance. And as a result, we correct 50 regexes as instance. And this is the result. Our tool, R3, could solve the 80% of instances. But unfortunately, in some cases, R3 could not solve the instance. For example, R3 could not be this instance. This is because to repair the instance, we need to remove the large fragment, but it requires large change from the original. So in such a case, R3 takes a long time. So in our evaluation, R3 could not solve the instance within a time limit. So in conclusion, I talked about these two topics, but I did not talk about these topics. But I think these topics are also very interesting things, so please check our paper. Thank you.
Thank you. All right. Plenty of room at the microphone.
Hello.
Hello.
Eric Koskinen from Stevens Institute of Technology. Interesting talk. One question I had was how far, if there's a limit to how far the repaired solution has to be from the input regular expression. I think on the previous slide you gave an example where it timed out, but like would it eventually find it?
Oh, can you repeat that?
Yeah, I was wondering if there is a some limit that's imposed as to how far the solution has to be away from.
I'm not sure, but yeah, it depends. I'm not sure, but I think yeah, it depends on the structure.
Like in this example, if it like ran, if you just let it run forever, would it eventually find a solution?
Yeah, if we have enough time, R3 will find the solution, but I'm not sure how long time it takes.
Okay, thank you.
Thank you.
So I have a question. Eric Ide, University of Utah. So you noted in your paper on one of your slides that there's no standard benchmark for this problem, and so you assembled your own by finding appropriate repairs in GitHub repositories, right?
Yes.
And I guess I was curious whether or not there should be a standard benchmark for this kind of problem. Would this be useful for other researchers who want to do regular expression repair? And if so, right, would you suggest that your benchmark is pretty good, or does it need to be revised or made bigger, or what would you do?
I think this benchmark is how to say good for the other researchers, because this is a real world database data set. So the regexes in the data set is collected from the actual GitHub results. So it may good for evaluating the performance of real world cases. So yeah, I think so.
Thank you. Thank you. Are there any more questions for our speaker? If not, let's thank him one more time.